I'm just thrilled to be here today to share with you the work that we've been doing at Keck Observatory over the last 18 years to study the center of the galaxy. And our original question was very simple. It was, is there a supermassive black hole at the center of our galaxy? And the answer is very clearly yes. And this gives us great evidence that these very exotic objects really do exist in the universe. And it gives us a great opportunity to study the role of black holes in the formation and evolution of galaxies. Now, this work has been very fun, and it's only been possible with high-resolution imaging on 10-meter class telescopes. And so this story, as Steve was saying, while interesting in itself, has also been very much a story of technology. And the way that we did this in the beginning was very simple. In fact, when we first started, no high-resolution images had been obtained at Keck at all. And we've made tremendous progress in the way that we obtain these images. So the questions that we can ask today are ones that we really couldn't even dream of when we got going on this project. Now, there are many people, actually I should have shown you this, there are many people that have been involved in this project. Let me highlight a few. My long-term collaborators, Eric Becklin and Mark Morris at UCLA, and Keith Matthews at Caltech, who you've heard about many times, and then a whole host of grad students and postdocs who we've had the pleasure of working with over the years. Now, the way I'm going to structure this talk is a little bit of past, a little bit of present, and a little bit of future, both thinking about the kinds of questions and the kinds of technologies we're using. Now, to start off, we're going to ask this question of whether or not there's a supermassive black hole. And to do this, the orbits of stars provides us with the most direct proof of a black hole. Now, to show that there is a black hole, our job is to show that there's a tremendous amount of mass inside a very small volume. Or to be specific, I need to show that the Schwarzschild radius, or the event horizon associated with a certain mass, contains that mass. So I only need to know two things, and that's the mass and a size. And there are a couple of different ways to do this. I'm going to, in all cases, use stars as little test particles to do this. And there's two different ways. I like to call this the impatient way to begin with, or the pre-tenure way. I don't have time to mess around. I need tenure. And that's, you just watch stars make a little bit of their orbit. So you measure a bunch of velocities, and then you statistically ask what kind of mass can give rise to those speeds. So this is a statistical approach, which means that one, it's based on a couple of assumptions, and two, you don't confine the mass as close as you could with individual orbits. So if you have patience, or if you have tenure, you can keep going and watch the individual stars make a complete orbit. And then, at that point, you're assumption-free, and you're much closer. So you've confined your mass to a much smaller volume, which means your evidence is a lot greater. Now, to do this, because I want to get to the smallest scales possible, to confine the mass to as small a region as possible, I need high-resolution imaging. Without high-resolution imaging, my images look like this. They're completely blurred. And with adaptive optics, or what we used in the beginning, you can get to the theoretical limit of what the Keck telescope affords you. Now, as I said, when we first started going on this project, it was very early in the Keck days, and while adaptive optics was clearly a vision for the future of Keck, it wasn't online. And so our first approach was to use, yes, NIRC, the camera we all know and love. And the idea here was to use this infrared camera and to modify it in a way that you could take very short exposures in a way that was at the right scale. So this was not designed to do this high-resolution work, but thanks to the efforts of, yes, Keith Matthews, who designed optics to make the scale suitable, and then also to the efforts of folks on the software side here at Keck, in particular Al Conrad, who made it possible for this instrument to read out very quickly. In the early days, we were so inefficient. We took one picture, 1/10 of a second picture every 10 seconds. So when Keck observatories used to put together their metrics of efficiency, they would leave us out of the equation. But we were getting data that you couldn't get in any other way. And that's the way it is often when you're working at the cutting edge. And so this technique of speckle imaging, where you take very quick exposures, is shown on the left. You see an animation that shows the actual data that we got. And the atmosphere does horrible things to you, but because you're taking such fast exposures, you can see, you can actually record what's happening. And then in post-processing, so the work is all in the computation afterwards, you can recover your high-resolution picture. So if we just expand out the box in the middle, that's the picture that comes out in the end. Now, these are animations I really love. This shows you a picture from every year, and it's the real data. It's not massaged. It's not an animation. It's really what we used to analyze or what we got out of our initial analysis. And hopefully, you can find in this picture my favorite star in the universe. Its name is SO2, and it goes around the center of the galaxy every 16 years. That's what I said too. Okay. But it took us a while to get there. So in the early days, what we did is we took a picture and you measured where they were. And this is, again, just the positions of stars in that central region, so a very limited part of our entire region. And we plotted a dot, or I think it's a circle there. And then I took another picture, which is, I think, the square. And you've got 2 points, you've got a line. You take a third point, you believe it. So this was the first report of velocities. You can actually measure the velocities on the plane of the sky or the speed. And you can do the statistical approach of inferring from those velocities the enclosed mass, the mass inside those stars as a function of radius. Now, this was our first claim that we had confined the mass to a region that was small enough that we should be fairly convinced that there's a black hole. But at this point, we're at a 10,000 times the Schwarzschild radius, so quite a bit larger than the theoretical limit. And there were plenty of people who were willing to come out and say, I've got other ideas about what this should be. And that means, of course, that you really need to keep going. And what comes next after velocities is accelerations. You keep going and you start to see them make the bend. But it turns out with just accelerations, what you can do is you can tell where the black hole is, and you can also tell that some of these stars might be on short periods. In fact, what you get is the density. You just don't know what radius you've confined the mass to. But it means that we have some idea that some of these stars might be on really short orbits. Now, at this point, I thought I would pause and say that while it looks like it's very obvious or easy that we should have done this, but this experiment was not in the Blue Book. So in fact, when I first showed up at UCLA, so thrilled to have access to the Keck telescope and wrote my very first Keck proposal, it was turned down. It was turned down because there was a sense that this crazy idea of speckle imaging wouldn't work at Keck, and even if it did, we wouldn't see anything. So I always tell the grad students, never take no for an answer, and keep going. So we got time in 1995, but this was the early days, and we were trying something, we were using the instrument in a way that it shouldn't have been used. So we broke it. And this was a real testimony to the staff at the Keck Observatory, because people drove up the mountain in the middle of the night and took this instrument off the telescope and put it on the deck. I mean, this is the middle of the night, and got us back online because we had a precious 2 half nights. So we did get our first measurement. That first dot was 1995. We come back a year later. What do we have? We have weather problems. Happens very rarely, but it did that year. But again, thanks to the amazing dedication of the Keck staff, they waited till the last wee hours of the morning and stuck with us, and it did miraculously clear. So we were very happy. And as Bruce and others have shown, these were the early days. We were actually at the summit, so we have our sweaters. We all look a little younger. That's on the left is Eric Becklin, and behind him is Mark Morris. Now, ever since 1995, we have managed to get data, and that's thanks to all these amazing people. This is just a few individuals that have been with us for the long run, that we've worked very closely with. I really feel like they're part of the team, and there are many, many others. The people that we don't get to see at night, the people who work very hard in the day, people like Barbara who make sure that we actually get on the telescope and get our at the right time. So we're really appreciative. And there's been a tremendous progress, and that progress, as you know where I'm going, is adaptive optics, and that's thanks to Peter Wazinowicz and Claire Max, as you heard this morning. So what does that look like for the center of the galaxy? So if we just look at the central region, the central arcsecond, which would be one big blur if there was nothing. On the left, again, it's the old animation. Put it in black and white to make sure that we understood that was the old. And then there's the new, and that's new, it's in color. So this is adaptive optics. And really, this is, in almost any way you can describe how well you're doing about a factor of 10 better. We see stars that are a factor of 10 fainter. We can position the stars a factor of 10 more precisely. And now, for the first time, we can take spectra, which gives us a tremendous amount of information, not only about how things are moving along our line of sight, which was missing from the images, but we get to learn what kind of stars that we're seeing in such close proximity to the black hole. Here's the movie that we've all been waiting for, the update. This is now actually even smaller, so I've been showing you on a side 1 arc second. So this is a fourth of the real estate, and we've made it smaller now because this image is this animation of how the stars have moved over the course of this work has gotten complicated. So let's walk through this. When a star has been found in the data, in the imaging data, it's trailed by a dotted line. And you might notice that stars miraculously appear about now, and that's because adaptive optics, it gets us deeper. It's also true that once with adaptive optics, we realized that there were more stars. We went back and worked much harder on the original Speckle data with new analysis techniques, and of course we know much more about where these stars are. And now we can do spectra. So once we have spectra of these stars, it's trailed by a solid line. So having said that, you can maybe infer which star is the most important star. In other words, why SO2 is my favorite star, because it's the one that goes all the way around, because it's the brightest of the short period stars, and because it's the brightest, it's the only one that we really have good spectroscopic information. That means that while I can use all these stars, the star that is, so to speak, the star of the show is SO2. All right, so this means that we've actually confined the mass to a much smaller volume. In fact, we've confined it to a region that is roughly the size of our solar system. This has actually increased the dark matter density by 10 million from the inception of this work. And that's what gives us the confidence to claim that there really is a supermassive black hole. And we're now, although you're still allowed to be skeptical, but the theorists haven't come up with an alternative yet. We're at 1,000 times the short field radius. And this plot, which shows density, dark matter density is a function of the dark matter mass. The job is really to get above that green line, because that green line is the lifetime for clusters of dark objects. In other words, you can be something else if you're below it, which is where all other galaxies, for the most part, are. Our galaxy has made it from the bottom to the middle point, which is the velocities, and off the chart with the orbits. So we can now confidently say that supermassive black holes do exist. And in fact, this is quite interesting, because if our galaxy has a supermassive black hole, and we are absolutely ordinary, garden variety, nothing special about us, the inference from that is that all galaxies harbor supermassive black holes. So if we sort of think about how we got to where we are, it's rather a fascinating story, because there are galaxies known as active galactic nuclei that made us ask this question in the first place. They made us ask that question in the first place because they produce an enormous amount of energy in the form of jets, and at the center there's light that's really unlike anything else, and we infer from that, or we thought or hypothesized, that it was matter falling onto the black hole that was driving all this energy. So this is about 10% of the galaxies. But really what our black hole is telling us is that all galaxies harbor supermassive black holes. They're just dormant or quiet, or I actually sometimes like to view them as black holes on a diet. They're just having a little snack. Now, what we At the beginning of this work, when we first came out, people were asking, well, which came first? Was it the black hole or the galaxy? It was sort of like the chicken or the egg problem. And what we know today is that there seems to be a correlation between the mass of the galaxy and the central part of the galaxy, the bulge, and the mass of the black hole. And what that tells us is that whatever formed the galaxy had to form the black hole. They have to form together. So they're very synergistic. And because that relationship seems to hold up over time, there must be a feedback mechanism between the black hole and the central part of the galaxy. So we really are left with this interesting question of what role black holes play in the evolution of galaxies. In our galaxy, because it's so close, the next closest galaxy is 100 times further away, affords us with an opportunity to really look in great detail at the processes that are ongoing. And there are two in particular that I want to look at in terms of what we're able to do today. One is we can look at that accretion flow onto the black hole. It's just a dribble, but it's an interesting dribble. And we also want to look at the stellar population around the black hole. In other words, to learn about how black holes and galaxies grow up together. So we have this unique opportunity to study the accretion flow. And before our work, it had only been seen at radio wavelengths. This accretion flow gives off light and light just outside the event horizon. Sagittarius star is the source that is associated with a black hole that's presumably associated with this, this accretion flow. This is a little animation of data that we took at multiple near-infrared wavelengths, so you can measure the color of the object, so you can see the stars, and then you can see where the black hole is. There's this thing that's very red. So first we get the first detection of this thing in the infrared. Second, we learn that it's very red. And third, that it's highly variable. The stars are actually stable. Again, this is real data, not an animation. And we have this opportunity to learn about the accretion flow by studying both the variation and how it correlates to other wavelengths. Now, I could say a lot about this because we've done a lot of work on this, but I'm not because I only have less than 10 minutes left. So I'm going to focus, and I intended to only say one thing, and that's this. And this is the most recent thing that we've been able to do, and I wanted to highlight it because it's the kind of work that you can only do at Keck because we now have adaptive optics on 2 telescopes, which means that we can take observations on both. In other words, you can ask for time on both telescopes. And we ran the imagers on both telescopes as fast as we could at 2 different wavelengths. And the fun thing here is that we see a small time delay, which is only 3 minutes, and you only see it in the decaying flank. This is fun because, of course, it contradicts all ideas about what you should have seen beforehand, and we don't know the answer. So I can't tell you, just to say this is unique to Keck. And again, probing things that we didn't know before. Now, speaking of probing things that we didn't know before and things that we're very excited about, there's a huge amount of excitement in our community about what might happen this summer. So it turns out you can't see the center of the galaxy all the time because the Earth goes around the sun, so there's a blackout time. And in a few weeks from now, it's opening night for the 2013 Galactic Center season. And what's been predicted to happen, or there's a discussion about, is that it seems like there might be a gas cloud that's only 3 times the mass of the Earth that seems to be headed towards the black hole, going through its closest approach, certainly within the next year. And when that happens, if it is really a gas cloud, it's going to be completely shredded, which means the black hole is going to see a fresh dose of a material, which may put it into a different state. So people are very excited about this. It's exciting, but it's controversial. It's controversial because that suggestion doesn't fit all the observations. So let me just briefly say, this is, again, the spectra that we're never supposed to show, but we have to show because that's got all the information. This is an emission line in different years, going from the most earliest to the latest, and it gets broader. That's evidence of an interaction, but the brightness of this line is not changing. So it turns out that that's not the prediction for a gas cloud. So this is putting a little bit of a question mark on what's going to happen this summer. It's definitely going to happen this summer. We are a little bit debating about exactly when, because it turns out it's very difficult to predict before it's actually happened. But more than 30 programs have been approved for this summer alone to watch this event. This may be the most observed astronomical event in recent histories, and we'll be there to watch, so stay tuned. Now, in addition to the accretion flow, we can also look at the stellar population. And let me really simplify this and say we can divide stars into two populations, old stars and new stars. And there's a prediction about the old stars and the new stars. The old stars, the prediction is around black holes, there should be tons of them. And the young star, there should be very few of them. And what do we see? In this picture, this depiction, the green stars are young and the red stars are old. So the exact opposite of the prediction. Again, kind of fun. And our orbits, as we go forward, have told us something very interesting. The young stars, once you get far enough out, form in a disk, or fall into a disk. And that's the important clue, because that tells us that this star formation must have happened in a pre-existing disk that doesn't exist today, because we simply don't see it, and you need high densities to get star formation to occur. So that tells us that our black hole was probably also being fueled much more rapidly when these stars were being formed just a few million years ago. Now, the lack of old stars, I don't have an explanation, which is why I have more words on the slide. So let me just say, actually, to keep this shorter, that's our next frontier. We really need to figure this out, because today we don't have the answer. And the reason this is harder is because these old stars seem to be located at much further from the black hole. So to get the kinematic information, you need to wait longer. The longer you wait, the bigger your horizon for the orbits. But you can also improve your measurements. So that just speeds things up. You also need to tune your spectroscopic observations to be more sensitive to the old stars rather than the young stars, which is where we focused. And in the modest future, tests of Einstein's theory of general relativity is something that we're very, very excited about. So let me focus on that. SO2, my favorite star, is important because if you can measure the effects of general relativity, and there are two ways you can do that, it gives you a unique probe of general relativity. You get 100 times closer to the event horizon, and you're working on a mass scale that's 10 million times larger than any of the other probes. And there are very, very, very few probes of this fundamental force. So there are only 4 forces, and this is the one that's the least tested. And there are 2 ways in which you can make the measurements. One is black holes are going to warp space-time. So you can measure both how the photon travels from the object to you, and that's the gravitational redshift. Turns out that's easier to detect, so that's what we're going to aim at first. And then you can also, that warping of space-time will also affect how the object moves. So that's the precession of the periaps. So relativistic redshift within our reach today, precession of the periaps not within our reach today. The next closest approach, where we have the opportunity to test the relativistic effects, is in 2018. So we are 2018 or bust. We want to be as ready as possible for this moment in time. And you can see this is the predicted difference in the radial velocities between the classical orbit and the relativistic orbit. And it happens over the space of basically a year and a half. So what I'm going to say is, what do we need? We need high cadence observations. So Barbara, what we want is a little bit of every night available. So we want the deployable tertiary. We want to be able to share easily with other programs. And if we can do everything that we're working on, including the high cadence, the improved precision of the reference frame and spectroscopy, this is within our reach. The precession of the periaps is not within our reach of today's technology, so you know what I'm going to say. What I want more than anything else in the future is the next generation adaptive optic system, so not one laser, but multiple lasers. So in conclusion, because I know I'm out of time, is that Keck has really been at the forefront of high-resolution imaging, and it has completely transformed our understanding of the center of our galaxy. We have definitive evidence for a supermassive black hole that's 4 million times the mass of the sun. This proves that supermassive black holes exist. And we have this unique opportunity to study the role of black holes in galaxy evolution. We're very excited about our future, both in terms of studying this interaction and in terms of studying relativity. And the obvious next big step is next generation adaptive optics. But before I really conclude, I really want to thank Keck Observatory for making this project possible. This has been an amazing journey and an incredible opportunity to work with the staff and the folks at Keck. It's a great partnership between multiple institutions, between people who build and run telescopes, build instruments, and the astronomers. So for that, I'm really grateful. I really have the dream job. And let me end with the latest animation that we made for this occasion. Thanks.